Next thing we'll talk about is something called the kinetic molecular theory. Kinetic molecular theory. Kinetic molecular theory. Hmm? Some days, but if I have a lab set up, he can't sit back there. So like tomorrow, I'll have a lab set up that he can't sit back there. Yes, if he's not, if he is, if I don't have a lab set up, then he can move back there and you can sit there. But you need to tell me.
It's already enough going on with that thing.
What?
They keep tapping. Hey, Robbie, are you okay with this?
I'm perfectly fine. I'm actually wide awake for once.
Okay.
No offense, not your lesson.
All right.
The lights all up in here.
Okay. Kinetic molecular theory. Here's what you need to know about the kinetic molecular theory. There are 5 basic assumptions. 5 major assumptions.
No, it's in your own third section that he had us aim for. The third section he had us aim for.
Yes.
I know, that's what he...
But you're required to know it.
I'm confused.
That's what section is.
5 major assumptions to the kinetic molecular theory.
Page 30,
Okay? But now, you can memorize those 5 major assumptions on page, I have it on page 15. What do you say?
I said 30 is like a card. 15.
Yeah, it's listed on the bottom of page 15 is where I'm looking. Yeah, okay, so there's a little inset box here too about that.
It's like summarized. Didn't you write this? I never know it's on this.
Okay. All right, so it's in 2 places. Yes, the one on page 30 is a little bit of a summary of what's right here. Okay? All right, the 5 major assumptions. Now, I'm not going to, how would I teach you? You want to do a quiz on this or something? I don't know. What do you want me to do to teach this to you? Okay, you're going to have to study this for yourself. That's the point.
Quiz,
You're going to have to memorize this for yourself. Okay? If you need to use flashcards, James, Skylar, whatever you need to do, you need to know these 5 assumptions. You also need to know why those assumptions exist, and that's what I want to spend the remainder of the class time talking about, is why those assumptions exist. So I'm going to let Shane in. Yes?
So when we have a quiz or test on this, like, are we going to have to write it down or what this meant, or are you going to have it in a bubble form where we...
It'll probably be a multiple choice question.
Well, it really could be either one. You need to know what it means so you can try to fix.
The first one is like gas particles only have mass but no volume.
Right.
But usually it's the other way around. Gas has volume but no mass. So it's kind of...
No. In order for it to be matter, it has to have both. So if we take that at face value, that gas particles consist of very small particles, each of which is so part. See, this is the explanation here on page 15. If all you do is look at page 30, you're going to have an incorrect understanding of why we can make those assumptions. Okay? And that's not a good idea. So I'm going to turn over to page 30, just look at that. Gas particles have mass but no volume. That's not true. That can't be true. If it's matter, it's got to have both mass and volume. That's a definition, or no, that's not. That's not a definition of matter. Actually, it is a way to determine if you have matter. That's a different thing, okay? And sometimes they talk, in physical science, they'll call it a definition.
But it's an equation to matter.
Yeah, it's actually not so much an equation as it is a way of determining if something is matter. If it has mass and it has volume, then it's matter. That's what, and I wish they wouldn't call it a definition because it really isn't a definition. A definition would be different. But we don't need to get that deep into it, okay? Not in here, all right? But that's not the whole story. The better part of the story is then on page 15. So if you haven't turned to page 15, if you might want to put your finger in both places, And that's the headline. This is the background information that you need to know.
Okay.
That they're really, really small. They're really, really small compared to the space between them. So much so that we don't even have to consider their volume. It's inconsequential. Okay?
What type of gas is we talking about?
Any kind of gas. Any gas at all.
Ideal means.
No, ideal, we're going to get the ideal in a minute, okay? We're going to get to that in a minute, okay?
I have a question.
Yes.
Is smoke a gas or salt?
It's what now?
Is smoke a gas or salt?
Smoke per se is tiny solid particles that form usually it can be either a colloid or it could be a suspension, okay, in air. That's what smoke is. Tiny solid particles. All right? They are very rarely actually dissolved. Okay? So it's not a solution.
That's going back to what, a science video that I watched about smoke getting to you, because it's like when smoke gets into your lungs, you see big particles getting stuck into your
Yeah. That's true. If you've seen those kind of pictures, you know what I'm talking about, right? Okay. Now, the reason why we can treat them like they have no volume is because the volume is inconsequential to their behavior.
What that mean?
Inconsequential? Doesn't mean it means it doesn't matter a whole lot to its behavior. Let's see if we can come up with a kind of example that will help you understand that. Okay? Let's everybody stand up a minute. Just stand up right where you are. I want you to face that back door back there. That back door. See the back door right there? Okay. Everybody see the back door? Pay attention. This is really important now. All right. I want you to take one baby step toward that door. Okay. You are on your way to Greenville, South Carolina.
Okay.
Now, how consequential was that baby step?
Not very.
But were you headed toward Greenville?
Yes.
Yeah, you were headed toward Greenville, but I mean that's like 30 miles away over there, and you've only taken one baby step.
We don't want to go.
Have a seat. Okay, so listen. Shh, have a seat. Have a seat. Okay. So listen, Shane. Need you at your desk, please. Okay.
Are you going to define ideal?
In a minute. I said I would later.
Get impatient with me.
I hate answering the same question 3 times.
No, I asked you one. No, that was me.
You know what? So I got to stop and answer every person's question, the same question. What is it? 20 times in here? No. No. What? Yeah, you get water. So, listen. That one tiny step, James.
I can't concentrate.
That one tiny step was inconsequential to a trip to Greenville. Doesn't really matter much, does it? Okay? So, in the same way, the size of a gas molecule is so small that the volume it takes up is inconsequential to the overall behavior. Now, it would matter if we put that gas particle or those gas particles under extreme pressure. Then the volume of the gas makes a difference. The gas particle makes a difference. But unless I'm under really extreme pressure or really low temperatures, the volume of the gas doesn't make much difference in the kind of behavior we're going to be looking at in this unit. What?
No, I'm not trying to be funny. Like it seems like your fingers are swollen up.
They're not swollen up. Let's just worry about this right here, okay?
It's been bothering me.
I'm checking out for your health.
All right, I appreciate it, but let's stay focused on chemistry, okay? All right. Collisions of gas particles with the walls of the container holding them and with each other are perfectly elastic. Now, if you look on page 30, it doesn't quite say that, does it? It says gas particle collisions are perfectly elastic.
Like, if you tested us, would those be like the things we have to, we'd have to put a summary of, all the 5 things?
It depends on the test, on the test question. You kind of need to know both. The other's a headline version, but you kind of need to know what they mean. This is more what they mean.
I thought we was coming up with a way we should remove them. Is there one?
The headline version on page 30 will help you remember. But when you remember the headline version, you need to also understand the more complex version.
Okay.
Okay? All right, now listen. Shh. There is no such thing as a perfectly elastic collision.
What you mean?
Perfectly elastic. If I take a rubber ball and hold it up here, say 4 feet above the floor, and drop it, where does it bounce back to?
Like
halfway.
It won't come to my hand.
It might not
It might come awfully close, but it's never going to come as high as my hand. And that's because the collision with the floor releases some energy into the floor. If we had a really good thermometer in that floor, the floor would get warmer. And so would the ball. Okay, so some of the energy is lost to heat due to friction. Exactly right. Okay? So there is no such, in much the same way, there is no such thing as a perfectly elastic collision. However, the kind of collisions that gas particles have are so close to being perfect in terms of the big picture, it doesn't make, we can ignore the loss in energy because it's so small, we can't even measure it hardly. Okay? It's not worth trying to deal with because our problems aren't going to deal with, 500 places past the decimal. We're going to be dealing with numbers bigger than that. And so they'd round off anyway. Yeah, James?
What about some small basketballs that you get out of
Yeah, they like go harder than
Like, what are they made out of to do that?
I don't know, and it doesn't really matter. The point is they will not bounce back as high as they drop from. Yeah.
What if you, kind of toss it down?
That's different. That's putting more energy into it. We're talking about a simple drop. We're trying to help you understand what a perfectly elastic collision is. A perfectly elastic collision would be one where all of the energy that the particles had going into the collision, all the energy follows that particle after it leaves the collision. And that's impossible. Okay? All right. So molecules are in constant random motion. Now this may be the one that's closest to being true, but even it isn't true. Because in any set of particles that are constantly moving around, it's quite possible one of them sitting dead still. But most of them, the vast majority of them, moving around. Okay? And what we actually do is treat them as having the same motion. But in fact, those particles are moving at different rates of speed. They're random motion. What we do is we treat them as if they have one motion when actually we're talking about an average motion. Okay? No forces of attraction between particles. Well, we've already done all the polarity stuff. You know that's not possible. All particles have some attraction. They have either temporary polarity, causing London forces, so they all have stickiness, or they have permanent polarity, but all gas particles have some attraction. The thing is, in a gas, the particles are moving so fast and bounce off each other with such intensity or force that the amount of attraction or stickiness is virtually inconsequential. It's so small compared to the big stuff of them bouncing off each other that it doesn't matter much. Our math is easier if we ignore those tiny, tiny, tiny things and go to just the big things that affect our equation. Okay? Average kinetic energy, we said, is the same throughout, which is not entirely true. Okay? So, the fact of the matter is, while none of these are true, all these things we talked about are so small compared to the big things that really make a difference, like the tiny step versus actually getting somewhere to Greenville. Okay? The little tiny things don't matter a whole lot. And we could ignore them. That's what these 5 assumptions are. We're ignoring the little stuff. Okay? We're ignoring the little stuff. So if you get up and walk out of this room, you're ignoring all the bumps on the floor. Okay? There are lots of bumps on the floor. But you're so big compared to the little dust particles or imperfections in the floor, it doesn't matter. Okay? Does that make sense? So we're ignoring the little things that don't matter here. And that's what those 5 assumptions are about. Does that make sense? All right. Now, yes. If we make that assumption about a gas, then that gas is ideal. All right. Now, Amber, Todd, I'm answering your question. Okay? If we assume all these things to be true, if we ignore those little tiny things that don't make much difference in our calculations, then we have an ideal gas. Okay? And it exhibits what we are going to call ideal gas behavior. If we ignore all those little things in the 5 major assumptions of the kinetic molecular theory, then we have an ideal gas. Okay? So an ideal gas is one that exhibits ideal gas behavior. Okay? Now, is there such a thing as an ideal gas? No, because none of these are true. But they're so close to ideal behavior that we can do the math a lot easier by doing it, by assuming it to be that way, okay? Is there any such thing as a perfectly flat surface? No. Because if you get smaller and smaller, you look down to it in a better and better magnification, under more and more magnification, eventually you're going to see there are imperfections there. There's no such thing as a perfectly flat surface.
That's what they do.
That's right. That's right. Okay? So, in the same way, there's no such thing as an ideal gas. We treat it like an ideal gas because it makes the math easier. Because the imperfections in our floor don't really matter. They're inconsequential to us getting out and walking to lunch. That make sense? All right, then. Now we can get to these gas equations that are based on this ideal gas behavior. We get to these gas equations that are based on ideal gas behavior. And you need to know this. Amber, you need to know this. All of the equations we will deal with in this class, all the equations we will deal with in this class, are assuming that the gases are ideal. There is no such thing as ideal, but we're assuming they are because the little things don't matter to these equations. Does that make sense? All right, one other thing you need to know, besides the fact that all of these equations we're going to be dealing with are assuming ideal gas behavior. The other thing is that ideal gas behavior, well, all gases behave pretty much ideally unless. All gases behave pretty much ideally unless they're under extremely high pressure or extremely low temperatures. Extremely high pressure or extremely low temperatures. All gases pretty much exhibit ideal gas behavior for us, unless they're under extremely high pressure or extremely low temperatures. Yeah. But I don't know. But you need to be writing notes whether it's in the packet or not, because
I know it can't see, but I'm.
there you go. Okay.
I want to highlight. I think it's like 20.
Huh? Very, very extremely high pressure and extremely low, low temperature.
Okay, I got it.
All right. So, the first of these gas laws is Charles' law. The first that we're going to deal with anyway is Charles' law. It's the only one we'll get to today. Okay? Charles' law. All right? Now what Charles' law says is that if you change the volume of a gas in such a way that the pressure doesn't change and the number of moles or the amount of gas doesn't change, and the only factor you're allowing to change is the temperature, then any increase in volume, any increase in volume also increases the temperature. Any decrease in volume decreases the temperature. So that volume divided by temperature equals some constant. Yes? What? What last year?
The one that he's supposed to take after this class.
Oh, physical science?
Yeah, that's
well, good. It's not a physical science subject, but some physical science teachers. It used to be,
Constant.
but they moved it up to chemistry. Okay? Well, great. Then we're way ahead. Okay? All right, so if I have an initial volume and an initial temperature, then if I change the temperature,
You got it.
the volume has to change to correspond with that. So that you always have this kind, and this is the kind of relationship that's going to work for us the most in here. Okay? This is the form of this equation that is going to help us the most in here. Okay?
I don't understand like what Charles state. Like he was trying to word it for us. That's an algebra, isn't it?
Yeah, this is algebra. This is algebra problem. Sure.
Yes, something like that. Why?
What Charles found was that if you increase the volume, assuming that nothing else changes, and that's important, nothing else can change. You can't change the pressure. You can't change the amount of gas, which corresponds to the moles of gas. You can't change those. As long as you don't change those, if you change the volume, the temperature is going to change with it, and in the same direction. So that if volume goes up, temperature goes up. If temperature goes down, volume goes down. Okay? And you want to see if it's true? Blow up a balloon sometime, stick it in the freezer.
Oh my God, what's going to happen?
Huh?
What's going to happen? Oh my God.
Well, let's see. You blow up the volume, you blow up a balloon, and it's at room temperature, and it's this size. Okay? If you decrease the temperature, what's going to happen to the volume? The ball, if you leave it in the freezer, the balloon should shrink. Try it. Try it. Try it.
How long will it shrink?
Huh?
How long will it
Until the temperature in the freezer. I'm trying to answer a question. Until the temperature in the freezer and the temperature in the balloon are equilibrated. That has to be the same. Okay?
So will the balloon still
I like that
be
word.
over the ice?
It depends on how tightly you blow up the balloon and how strong the balloon wall is. A lot of things factor into it, but you should be able to see some change in the volume.
Oh, really? So
Okay.
what if you take it out of it?
In fact, if you want a better example of it, take a Ziploc bag and blow it up and seal it. Because it doesn't, you're not stretching the balloon, you're not stretching. Can I finish first, please? You're not stretching the wall of that Ziploc bag to get it to blow up. Okay? And when that volume shrinks, you'll be able to see it a lot better. So try a Ziploc bag in the freezer. It's better than a balloon if you want to see the behavior.
Yeah, like.
What now? Well, Ziploc bags don't expand. They don't stretch. That's what I'm saying.
I thought you meant to fill the balloon with water.
No, fill it with air. I'm talking about gases here.
When you put food in Ziploc bags in the freezer, the Ziploc bags packs down to it. There's like no air. You just see a leak.
Well, you think so, but in fact, it does have air in there. It's just
I
contracting.
know what I'm talking about. Like I know what you mean when you say.
Mhm.
You say you run.
All right.
Chuck, I like the attitude.
Now, here's the thing. Listen carefully. This is important. The temperature must be in Kelvin. You cannot do gas law equations with temperature in degrees C. Okay? The temperature has to be in Kelvin. Get out your test references. Get out your test references, and you will find this equation on your test references, and you will also find the conversion between Kelvin and Celsius temperatures. So if you've got a temperature in degrees C, you have a temperature in degrees C, you add 273.15 to that, and that's going to give you temperature in Kelvin. If you have temperature in Kelvin, you're going to subtract 273.15, and that'll give you the temperature in degrees C.
So that was fair.
What?
Without, like, do you ever have to do Kelvin, Fahrenheit, or Fahrenheit?
No, we're not going to do Fahrenheit conversions at all. Okay, that's the English measurements, and that's English measurements. We're not going to do those. Okay? All right. The other thing I want you to know is this, and this is really important too. with all due respect to your math teachers and your algebra teachers, we will not be using cross, multiply, and divide in this class. We will not be using cross, multiply, and divide in this class. Okay? When we get to more complex equations, they don't work. Okay? And students make big mistakes trying to make them work. We will not be using cross, multiply, and divide in this class. Okay? Alright, so suppose we have a volume that is 2.5 liters of gas. And I'm going to go ahead and give you a temperature in Kelvin. And say we have a temperature in 300 point, with a decimal place there, K, meaning that's a significant zero. And we change the let's change the temperature to 350 with a decimal place K. I want to know what the volume is here. Okay? I want to know what the volume is.
You gotta put it.
We're going to plug in the equation. 2.5 liters for the volume. 300 K for the temperature. Over here we're going to put 350 K on the bottom. And the unknown, the V2, is on the top. And we don't do cross, multiply, and divide. Here's what we're going to do. We're going to isolate the unknown. We're going to do that by multiplying this side of the equation by the inverse of this. 350 K over 1. And what we do to one side, we must do to the other. 350 K and put it over 1. Now the neat thing about this is, if I can find my red pen somewhere, I guess I'll use this red pen. This cancels out. And we've isolated V2. We've isolated the unknown. We also can cancel this K. And the cool thing is, liters measures volume. So we know we've set it up right. Okay? And so that's how you need to solve these problems. You set up a list of knowns and unknowns. You write down the appropriate equation. Plug in the knowns and unknowns. Isolate the unknown. Cancel. And finally solve. Hello? That's okay. Mm-hmm. Okay. Sure. All right. So can you solve this problem?
You just gotta multiply.
Multiply these, hit equals, and divide by that. Do it. Get your calculator out. Solve the problem.
Mr. Tanner,
Mm-hmm.
I think you heard her say this, but what's the C except you put instead of 3.15?
This is how you convert from degrees C to Kelvin temperatures, from Celsius temperatures to Kelvin temperatures. Those really shouldn't be used as variables. I've used them like variables there, but it's just a definition for you, real quick definition. Okay?
And when we get a problem, we don't already have the numbers for it, like the 2.5 liters.
Oh, I have to give you the numbers to solve for the unknown, sure. Yes. You got it? Well, let everybody else solve it.
I got it.
All right, there's 2 people that's got it.
I got it.
3 people. 4 people. 5, 6. Where's your calculator, Todd?
You got it in your hand.
Come on. Let's get out your calculator. Let's practice.
You got a minute left. You gotta get it.
What's the answer? So it rounds off 2.92? Okay. All right. All right, remember,
Is that a Y or a B?
you're supposed to be studying the unit handout. Study the unit handout. Okay?